Okay. Bharat, are you there?
Yes, sir. We can start now, sir.
Okay, good. So, who has joined? Okay, one Gattadalli Nandini has joined. Hello, Gattadalli Nandini. Welcome. Do you have any clarifications, doubts? You can unmute yourself and ask, please.
Dear sir, actually, I am finding the proceedings very well. The lectures are very nice. So, doubts are also there certain times.
Please ask me, madam. Whatever possible, we'll explain now. Please ask.
Sir, actually, the entire course, no, sir, this
Hmm.
concepts,
Hmm.
is it the same thing repeated in NMR for chemists? Or is there any changes
Almost
in the course?
slightly different. So a few extra things are covered. Initial portion like introduction, chemical shift coupling, they are almost there. We cannot do anything. We have to introduce, and few extra things will be covered there. What is not covered here will be covered there.
Oh, so how advantageous is that then this then?
See, madam, what advantage? What I can say? See, every time when I give different lectures, I try to give new examples, explain in a different way. For example, if I consider a multiplicity pattern, why it comes, I explain giving different examples. And different times, I'll explain a conceptual in a different way to make the people understand, depending upon the background of the participants. So sometimes the title of the talk may be same, but the way I explain could be different to make you more understand. So it could be advantageous if you take it. Hello? Hello, Nandini? Please unmute yourself and ask.
Then I need to listen to those lectures also then.
If you listen, you don't lose much, madam.
Okay, sir.
You don't lose much. There will be overlap because when we have to
Oh,
give a course, first couple
uh,
of hours of lecture will be generally introduction, explanation, concepts would be different. That we have to
okay.
explain. That is common, but I explain in a
Hmm.
different style. So it
Okay.
is not bad if you can listen to it. It is always good for you.
Yes, sir. Sir, one concept I am always under confusion is this J coupling.
Yes, madam.
Actually, what can you please explain what exactly is this J coupling? Whether it is irrespective of proton spectra or carbon 13 or fluorine 19, whatever be the nuclear, what exactly is this J coupling, sir?
Okay. It is a good question. I'll explain to you. Just I will open a slide for you so that
Okay,
it
sir.
will become more clear. Okay, I'll open the
Yes,
slide.
sir. Yeah.
Are you seeing the slide now? Madam, are you seeing the slide?
Uh,
Hello?
It's
yes,
visible, sir.
yes, sir.
You are
Yes, sir.
seeing the slide, right? Okay.
Yes, sir.
I'll give you something information about scalar coupling for few
Yes, sir.
minutes. You try to
Yes, sir.
understand what I'm trying to tell you here. It
Yes,
may be
sir.
useful to you and your questions could be answered. If you have any doubt further, we can see in depth later. Okay.
Yes, yes, sir.
Okay. Now, where was my slide here? Okay. See here,
Yeah.
I'll give you some information about scalar couplings, which you are asking. What is
Yes,
this
sir.
coupling? Why it is coming? It is a magnetic interaction of nuclear spins where the
Okay.
energy is transferred through what is called a covalent bond.
Okay.
This one nucleus can
Yes,
interact with
sir.
the other nucleus
Yes, sir.
mediated through covalent bond.
Bond. Yes, sir.
That is a interaction. That means
Correction.
two nuclei should be J coupled. Means at
Okay.
least they should have a covalent bond.
Okay.
When there's a covalent bond only, and
Okay.
this spin can interact with this spin, and this
Okay.
spin can interact with this spin.
Okay.
Interactions are always mutual.
Okay.
In the sense, if I say A is coupled to
Hmm.
X is equally coupled to A.
Yeah.
Okay. That means
Yes, sir.
if this is coupled to this, if the interaction between this spin and this spin
Yes, sir.
is of a particular strength, it doesn't
Yes,
matter
sir.
whether it is this is coupled to this or this is coupled to this, both are same. Interaction
Same.
is mutual.
Sure.
Next point. What is the mechanism of coupling? This was your question, right?
Yes, sir.
It is a Fermi contact mechanism. That of more about Fermi contact, everything you understand in chemistry. For all the
Yes,
coupling
sir.
involving hydrogen bond, dominant is
Yes,
a
sir.
Fermi contactor. For example,
Okay.
a CH bond, if you take, it is
Yes,
connected by
sir.
a single sigma bond
Okay, sir.
with two electrons.
Okay, sir.
The magnetic moment of hydrogen, that with the proton,
Hmm.
can be either parallel or anti-parallel to the magnetic field.
Magnetic field.
This concept is known, right? For any
Yes, sir.
nuclear, if I consider the hydrogen nuclear spin, this can
Yeah.
be either parallel or anti-parallel to the magnetic field.
Magnetic field.
Two
Okay, sir.
orientations are there.
Okay.
Now, the ground state orientation is parallel to the field, that is lower
Ah.
energy.
G. Yes, sir.
And the energy which is, it is a preferred energy because it is lower
That's it.
energy. Other one
G.
is anti-parallel, that is another orientation, which is
Hmm.
very close to the bonding electron. Okay.
Electron.
More than the words, look at the figure here.
Yeah. Okay,
Now
sir.
I have one proton coupled
Hmm.
to carbon or proton, doesn't matter, another nucleus. There is a
Okay,
covalent
sir.
bond between these two.
Okay, sir.
Now let us consider a situation. The
Hmm.
proton magnetic moment is orienting parallel to this magnetic field.
Field. Okay.
Now what will happen? Because the Fermi contact term is the dominating interaction term, this
Then.
nuclear spin makes sure the electrons of this one also orient in a direction opposite to this, anti-parallel to this,
Not a balanced. Okay, sir.
because of stable state.
Stable state.
A parallel means unstable, okay? Anti-parallel
Yes,
is
sir.
stable. But why I have
Stable.
written both parallel here, not anti-parallel? That is because the electron has a negative magnetic moment. Electron is
And
negative, proton is positive.
okay.
As a consequence, because of that, it appears parallel to this nuclear spin.
Nuclear spin.
Hmm. This another electron, which is attached to this, surrounding this nuclear
Yes.
spin,
Hmm.
this electron, make sure this electron orients anti-parallel to this to give it a
Sir.
stable state.
State. Okay, sir.
This is because of Pauli principle.
Principal. Yes, sir.
This one, in turn, will
Hmm.
make sure this will align this anti-parallel to this.
Stress.
Of course,
Okay.
because of electronegative, I made it parallel, but this makes
Yeah.
it anti-parallel to this.
Parallel.
That means
Okay, sir.
through the bonding electron, this
Hmm.
nuclear spin gave
Hmm.
energy to this electron and to this, and
Yes.
then finally to the nucleus.
Discuss.
You understood? That
Yes,
means
sir.
the proton which is orienting like this magnetic moment in a magnetic field,
Well,
make sure the carbon which is coupled to this one bond coupling is there, one bond valence bond is there, will
there.
make sure that magnetic moment is anti-parallel to proton.
Down. Okay.
Okay. This is because of
Yes, sir.
Pauli principle. Two spins must be
Principal.
anti-paired. All those things we explained.
Uh,
Okay.
yes, sir.
Now we'll go further. Similarly, if it is anti-parallel orientation, it
Um,
makes this electron, again, this carbon nuclear spins orienting like this. Either
this
it's parallel or anti-parallel, doesn't matter. Here in
doesn't
this
have
case, I took this nuclear spin parallel to the magnetic field. But then
field
carbon nuclear spin is anti-parallel to that. Similarly,
that.
if you take anti-parallel proton magnetic moment, but the
Right.
same source, carbon is anti-parallel to this.
Professor
So
parallel
this is a
this.
mechanism. Okay.
Yes, sir.
So this is a
Yes,
very
sir.
important mechanism that takes place because of the interaction of the nucleus
Mhm.
means through covalent interactions,
Actions
which is covalent bonded,
on
where
that
we have two important terms coming into picture, Fermi
picture.
contract term and Pauli principle. These two
Principal.
play a dominant role.
Yes, sir.
In other words, we will say the magnetization of one proton is
Yes.
transferred to other nuclei. It could be proton,
Mm.
carbon, fluorine, or any nuclei,
Nuclei.
mediated through what is called covalent bond.
Covalent bond.
Okay? This is
Yes,
J.
sir.
This is
Yes,
mechanism
sir.
is called J coupling.
Coupling.
It is called
Okay, sir.
scalar coupling.
Coupling. Okay, sir.
You understood, madam?
Yes, sir. I understood.
Okay, very good.
Yes, sir.
Anything else you want? You have any other doubt?
Yes, sir. See, recently you spoke about the spin echo. Now, you said here in the spin echo, you told it shifts, refocuses the chemical shifts, but it will, if it is a homonuclear, it will not refocus the J coupling. If it
Correct.
is a heteronuclei, it will refocus the J coupling. Thoda, I mean, there is a bit of confusion is there in that explanation, sir.
Okay. So this is in which course? Is in advanced NMR course you are talking or in the concept and
Same,
chemistry?
same course what we are teaching in the, actually, I'm referring to the previous year's course. I'm
No,
see,
no,
I
no,
have
that's okay,
registered for
madam. No, no, there
uh,
are a couple of courses going in parallel. Are you
uh,
talking about these concepts and spectral interpretation course or advanced NMR, solid state NMR, everything is discussed? Are you
no,
talking
no,
about
no.
that course? In this
Present
course?
course concept. Yes,
Okay. So you give me 1 minute time. I'll open the slides and explain to
yes,
you
sir.
how this pin echo works.
Yes, sir.
Okay. So
Yes, sir.
in the meantime, let us see. If I will start that, it will take about 5-10 minutes to explain. If there are any other
Okay, sir.
values, the participant, if they have questions, will answer that. And then I'll come
Yeah,
back
okay,
to
sir.
you to explain what is
Yes,
pin
sir.
echo.
Okay, sir.
Okay.
Yes, sir.
So let us see who else is there. Dell. Who is Dell? I don't know.
See, spin, I will tell something. Spin echo is like that.
Yeah.
Suppose you gather 100 people in one line and ask them to run. Hello, madam Nandini?
Yes, sir. Yes, sir.
Suppose you gather 100 people in a line, in a row, and you ask
Yeah.
them to run. So they will
Okay.
run, but it is not like they will run with the same speed. So
Yeah.
they will start scattering. So
Yes.
if you take a section of area where how many people are there, you will see very less
Okay.
because you will not see 100. But in the beginning, if you see that line, you will see hundreds. So that will be more people, right? But
Yeah.
afterwards, suppose you take the same cross section and you will see only few people into that.
Oh,
But with the same time, if you say them go back,
okay.
and after the same time, whatever the time you have given earlier to run, and afterwards you give the
Mm.
same time to go back, and you
Mm.
take the screenshot where the line starts. So you
Okay.
will see the like 100 people, nearly 100 people, right? So
Yeah.
that is how spin echo works. When we allow the spins to rotate freely, rotate after bringing back to the XY plane, then they
Okay.
start processing, means they start running. So all
Mm.
chemical don't have same chemical shift, means precession is not same. So that's
Mm.
why they get dephased, means randomized, means you will see less signal at that time. But if you say you put a pulse which say them to go back, right?
Okay.
Then at a time they will appear exactly same, means with that pattern whatever earlier was by the dephasing. So that is the spin
Okay.
echo. So now sir will explain you. Now it's open.
Okay, that's good actually. What Sandeep said is already almost it is the
Okay.
similar, same explanation, but I'm going to give
Mm.
you through some slides.
Yes, sir.
Okay. See what is spin echo? I will
Yeah.
coming in the way. Okay, now it will be fine. See, I'll look at this one. What is a spin echo? This is important. This is
Yes,
a
sir.
two-pulse sequence.
Okay.
In NMR, we always use 90 pulse, 180 pulse, 45 pulse, varieties of pulses. You know that. I think we have
Yes, sir.
discussed this in the course. In one of the courses, I
Yeah.
explained to you about chemical state evolution, J evolution, what is 90 pulse, what is one, everything I've explained, I think. I hope you know that.
Okay.
So what is
Okay.
going to happen here? This is all too much for you. I don't want to explain to you. Consider an
Ah,
example like this. I apply a
okay.
90-degree one pulse. What will happen?
Mm.
All the nuclear
Mm.
spins will come to x-axis. If I apply a
Yes.
90-degree pulse on y-axis, all the
Yeah.
nuclear spins which were in z-axis will come to
Yeah.
axis. And then
Okay.
after some time, what will happen? They will not keep
Mm.
it.
Okay.
They will do as Sandeep explained to you, they will start
Ah,
defacing. That means if you
okay.
consider this as the axis, some will go
Oh,
in this direction, some will go
ah,
in this direction.
in this direction.
Okay, and then we call in
Oh,
NMR jargon, some are
ah,
going faster, those who are blue here are going faster,
okay.
and the red ones are what is called the one which is going slower. That
Slower.
means
Okay.
the velocity of the spin's
Yeah.
movement
Okay.
are
Okay.
different. One is faster,
Ah,
other is slower. That
okay.
will explain more later. Then what
Okay.
happens? They keep moving like this. Allow them to move for
Okay.
some time.
Yes.
They keep on moving. And then after
Moving.
some time, I apply
Mm.
180 pulse.
Okay.
What will happen? It will completely get reversed.
Just
Slow
okay.
moving becomes fast. See, red and blue get interchanged.
Yeah, exchange.
Slow becomes faster, fast
Ah,
becomes slower.
slower.
Okay, and that depends
Okay.
upon how I am rotating. I am rotating like on the x-axis like this. I am rotating on the
Oh,
y-axis like this. Doesn't
like
matter. Both
this.
are possible. I have to
Okay.
taken here rotation about
Yeah.
x-axis. All right.
X-axis.
What is the effect of this? This
Mm.
fast and slow got interchanged.
It has changed.
Now wait for the same time.
Okay.
Here you waited for some time
Yeah.
and then applied 180 pulse. Let us the time is let's
Okay.
say 5 microseconds.
Yeah.
Now
Yes.
wait for the same 5 microsecond, apply another pulse, and no, don't apply pulse. Wait for another equal amount of time and start seeing the signal. What was coming here, 180 pulse
Yes.
reverses it, and then it forms a echo like this.
Like this.
And then this is a very simple argument, but understanding is more difficult. It is not easy to explain like that. Diagrammatically, it is like this. But simply what is
Okay.
happening here in this case is, this is all more important, more about phase loss and everything, too much for
Ah.
you. But you don't worry.
Ah.
I'll consider an example of homonuclear case which you were asking. That was
Yes.
your doubt, right?
Yeah.
I'm
Yes,
considering
sir.
chemical shift refocusing in homonuclear spin case.
Plus minutes.
I have two no homonuclear spins, two protons,
Yes.
homonuclears.
Yes.
If they
Yes.
are A and X means chemical shifts are different.
Steps are different.
If the chemical shifts are same, I will call it A2 or A1 or
Yes.
sorry, A prime like that. Where in fact I
Okay.
have written A and X, chemical shifts are
Yes.
different.
Different.
Now, let us say there are fast and slow moving components. I told you.
Nice. Yes,
Slow
sir.
moving they have a less frequency by small amount.
Wow.
Fast moving have a slightly higher frequency by small amount.
That's it. Wow.
That's all. You remember that.
Yes, sir.
Now, this is diagrammatically what is happening like this. Slow
This
and fast moving with a different frequency. Slow
consists
moving and fast moving. Now I interchange it and wait for
that
some time. Where I started, I came back to the
mm,
same point.
point. Okay, sir.
Look at this one. Both
Yes.
fast and slow moving were on the x-axis.
Success.
X-axis. After some
Yes.
time, they were moving
Yeah.
like this. When
This
I apply 180 pulse, they got
pulse
interchanged.
change.
I wait for the same amount of time here.
Yes,
Then they come back to the same place.
same place.
Like our Sandeep explained, ask
Yes,
people to stand in the queue
queue.
like this here. There are several
Yeah,
people standing in the queue. Ask
queue.
them to keep running.
Yes,
Some will be, let us say, moved faster. Some would have moved
turn
slower. They are not at the same
yes,
distance. Depending
sense.
upon their speed, they will have different
Yeah,
positions.
sense.
Correct? In the
Yes,
running race, you can see
yeah,
you would have seen in the running race in the Olympics, all people will be running. But some will come first, some
yes,
will come second, some will come third, like that. They
that
are at different
yes,
positions.
sense.
Now, a 180-degree pulse means what happens is, I will immediately ask them to turn back wherever they are.
Yes, yes,
So many people, let us say, standing here, I mean,
yeah,
here, they started moving, one is
yes.
here, one is here, one is here, like
One
that.
second, one second.
I will ask them to in the same place, wherever they are standing,
Just checking.
turn backwards.
Yes, yes,
You understood? That is
yes, sir.
exactly the effect of 180 pulse.
What did I grab?
Then I
Okay.
ask them to run back with the
Yes.
same frequency, same
Let's
speed.
see.
Then what will
Yes.
happen? The person who was faster moving, who have moved this much distance, will come back to the same
Yeah.
place. The one who has moved this
Place.
distance will come back. One who has only
Yes.
moved this much distance will move the only same
Distance.
distance. So
Okay.
wherever they are, you ask them to turn back and go back with the same frequency.
Let's
All of
see.
them will come back at the same place where they started.
Place. Taking.
This is
Okay,
what is
sir.
called refocusing.
Send.
You understand? That
Yes,
means
sir.
wherever they started, wherever the spin
Yeah.
started, along
That
the x-axis after 90-degree pulse,
this.
before evolution like this with the time, they come back to the same place after
Place.
180-degree pulse and waiting for the same time.
Plus.
This is what is called refocusing, or in other
Send.
words, we also call spin echo. And more about other things, spin echo, why it is not going to be spin echo has refocus chemical shifts here because different
Yes.
spin A and X have different chemical shifts. Nevertheless, it will come
Yes.
back to the same place. That's why I said
Yes.
chemical shifts, spin echo refocus the chemical shifts,
Instant chemical
but it will
shifts.
not
Okay, sir.
refocus J coupling. That is much more to
Okay.
explain for you. I will not explain that, but I'll in the next class when you are in
Okay,
this
sir.
course which is going on, I
Yes,
explain these
sir.
things in detail,
Okay, sir.
how it works and how it happens, how the J modulation takes place, what happens if it is electronuclear spin, like you are
Okay.
asking me,
Yes, sir.
heteronuclear spin, what happens like this. So all those things I will explain to you. If I take
Yes,
heteronuclear
sir.
happens, homonuclear, what
Okay.
happens, all those things.
Thanks.
This is a big course,
Okay, sir.
and
Yes, sir.
this itself will take more than 1 hour or 1.5 hours to explain. But you just
Okay, sir.
imagine the concept of this. You attend the
Yes,
class,
sir.
you will
Yes,
understand.
sir.
Hmm?
Okay, sir. Okay,
Right.
sir. Thank you, sir.
Right. This is a lot more I have explained. Of course, what I showed is different. I have been
Yes, sir.
improving the slides every now and then because I don't, I'm now retired sitting at home, I keep changing it. I have improved
Okay,
this thing.
sir.
But what is shown in the
Okay.
class is different.
Okay, sir.
But anyway, this is new versions.
Okay, sir.
But the concept is same. Idea is same.
Yes, sir. Okay, sir.
So any other questions, madam?
Sir, the say one basic question.
Hmm.
Uh, we have inequivalent protons. Say
Hmm.
example CH3, CH2, CH.
Hmm.
And if there is no coupling
Hmm.
between CH3, CH2 and CH,
Hmm.
then we will have just the interaction splitting, that is CH3 will split the CH2 into triplet,
Madam,
CH2
when you
will,
said there is no interaction, no
uh,
splitting. CH3 will
okay,
give a single peak, CH2 will give a
yeah,
single peak, CH will give a single
okay,
peak. Only when there's
okay,
interaction, we call it as
yes,
decoupling mechanism is present between them. CH
them,
is coupled to
okay,
CH2, CH2 is
yeah,
coupled to CH, or CH is coupled to CH3, we have splitting, multiplicity pattern. If there is no
okay,
interaction, Even though they're chemically inequivalent, means at the respective chemical shift, you get only one peak each.
Here, one confusion will come about the coupling strength.
Hmm.
See, if the J coupling is strong, then
Hmm.
it is a strong between CH3 and CH2,
Hmm.
then CH2 and CH is weaker. The first will be the splitting of CH2,
Hmm.
then CH. So it will be like a triplet of doublets, like.
Okay, but I don't know whether you attended this J coupling. Have you already attended the J coupling splitting mechanisms?
Yes, sir.
When
Yes,
did
sir.
you? Is it covered already in this course?
Yes, sir. In week 4, lecture number 26.
I see. Okay. There you must have understood. I have explained to
Yeah.
you. When you want to understand the multiplicity pattern splitting mechanism, it
Yes,
doesn't
sir.
matter the order in which you take for understanding the multiplicity.
Okay.
For example, you said CH2 is coupled to CH3 and CH with different
Yeah.
couplings. One is
Yes,
more
sir.
coupling, other is less coupling.
Less coupling.
Okay, let us consider example. CH2 is coupled to CH3.
Okay,
I'm
sir.
looking CH2.
Yes.
What is the pattern you get, madam?
CH2, if it is coupled with CH3, then you will get a quartet.
Exactly. If CH is also coupled to CH?
Then doublet.
Exactly. Now your
Yeah.
question was, let us say couplings are different. CH3 to CH
Yes.
coupling is larger, let us say 20 hertz.
Yeah.
Then
Okay,
that will
sir.
be a quartet of larger separation. Each peak size is
Yeah.
separated by 20 hertz. It is also
Yes.
coupled to CH
Yes,
simultaneously.
sir.
Then it will be,
Yes.
let us say, 10 hertz coupling.
Yeah.
Then each line of the quartet will become a
Yeah.
doublet
Okay.
of 10 hertz each.
Okay.
Now the question is, it is called quartets of doublets, not doublet
Doublets.
of quartets. If this coupling is
Okay.
larger, CH2 coupling to CH is larger, then it is doublet of quartets. Otherwise, it is called quartet
Yes,
of
sir.
doublets. Fine,
Doublets.
fine. Let's
Yes,
forget
sir.
about that. Now coming to your
Yes, sir.
question.
Yeah.
If I consider CH2 coupled to CH3 first, I generate
Yes.
a quartet. Then I'll
Yes.
begin coupled to CH.
Yes.
Then it will become another, each line will be a doublet. Fine.
Let
It is a quartet of doublet. We'll
doublet.
come back to another mechanism. I'll consider CH
Yes.
coupled to CH2 first. What will
Okay.
happen? It will be a
Uh,
doublet.
Triplet.
No,
Uh,
CH2 is coupled to CH. I'm looking at
it
CH2.
will, yeah, it is
It-
doublet.
now I consider coupling to CH3. What will
Yes.
happen?
Doublet will
Each
become
line will become
quartet.
a quartet.
Quartet.
It is also called, if the coupling of CH2 to CH3 is larger, this is also called quartet of doublets. What I'm
Doublets.
trying to say is, whether you consider CH2 to CH3 coupling first or CH2 to CH
Uh,
coupling first, to generate the multiplicity pattern, splitting
um,
pattern remains invariant.
okay, sir.
In either way, if you want to generate
Yeah.
multiplicity pattern, consider this first and make it
Yeah.
doublet and then quartet, or consider CH3
Yeah.
first, make it quartet and then doublet. Doesn't
Yeah.
matter which order you take. The order of
Okay.
interaction which you take into account for generating multiplicity is immaterial. The
Serial.
pattern remains same.
Same.
You
Okay, sir.
understood it?
Yes, sir. Understood this part.
In fact, I don't know whether I gave an example for you, whether if you have seen that. I would have given a lot of examples for that.
Yes, sir. Varying of A. One proton is signaled as A, then another as Y, and another two as X.
Hmm.
Varying the strength, JX varying to JXY, the AY is varying with JXY. So we have given quite number of examples there and
Okay,
explained.
very good, madam. You have followed it. Fantastic. There, I have taken one special example to ask this. Somebody asked the question, so I prepared a slide to show. Either you
Uh,
take this one first. First, you split CH2 into a CH3 by CH3 into a quartet, and then CH
Hello.
doublet by
yeah,
CH, or first
yeah,
split by
Bolo, bolo,
CH into
bolo.
a doublet and then CH3 by CH3 into a quartet. It doesn't matter. I have shown the pattern remains
Can
identical.
critical. Okay, sir.
Clear?
Yes, sir. Understood this course. Sir,
Oh.
can you mention any downloadable book for NMR for this particular course?
This somebody asked me
Concepts.
earlier. I have brought this now. This is a book.
Okay. NMR
NMR
data
Data
entry.
Interpretation. It is a
Okay.
fantastic book. Anybody who
Okay,
wants
sir.
to learn NMR, I would say you possess this book. This
One
author
second, sir.
really has explained everything so well. Very good.
Okay, sir.
In fact, many of the
It's
examples I'll take from this book to teach. It's a very good book. It's a book by
mail. Uh,
NMR Data Interpretation by Neil Jacobson.
okay. Publisher, sir.
Publisher Wiley.
Wiley. Okay, sir.
You remember that NMR Data Interpretation by
British
Neil Jacobson.
Hobson.
It is available, I think, in Amazon or somewhere you can buy it. It's a very good book.
Okay, sir. Okay, sir.
It is also available soft copy somewhere, downloadable
Yeah.
on the web. But I would prefer you buy a hard copy. It's a very good
Yes, sir.
read.
Okay, sir.
It is like this. I showed you, fantastic.
Yes, sir.
A hardbound
Yeah.
copy.
Okay,
It is easy to use it
okay,
as a
sir.
pillow also while reading.
Okay.
If you don't understand,
Yes, sir.
at least it can be
Yes,
used as a
sir.
pillow.
Sir, during the course, sir, my personal request is please show us the recording of NMR spectra, one-dimensional and two-dimensional. Sir, just a demo.
Madam,
Um,
this is a recorded course already. Now it
oh,
cannot be done. This
oh,
was recorded at the NPTEL office at Bangalore long ago,
oh,
1 or 2 years
oh,
back.
okay,
So the recorded version
oh,
being shown, I cannot show
okay.
it for you right
Uh,
now. If you want to know how to record spectrum, where are you now?
uh, I'm in Mumbai, sir, Thane.
Mumbai, Thane. You go to TAFR
Oh,
center. Otherwise, if you go to Pune, our Sandeep who is sitting here, he is an expert. He
oh,
can show you in
okay,
ICER.
sir. Okay, okay, sir.
Now online I cannot show. It is not possible. It is a
Okay,
recorded
sir.
course.
Okay, sir.
You got the point, madam?
Because, yes, sir, I got it.
Hmm.
Instrumentation also, if you know, it is better. Anyway, I understood this.
No, I have already instrumentation. I have not discussed in any of these courses. But
Ah,
I think in one advanced course, I talk about NMR, various parts of the NMR spectrometer. I
okay,
have discussed some electronics also, I think so, in one course.
okay.
About 2 classes
So,
about electronics of NMR instrument I have discussed. But
okay,
not in
sir.
this chemistry course.
Okay, sir. This is concepts and spectral analysis
Yes, this is
course.
only to understand the concept. How do you analyze the spectrum to get the structure, etc. That's what was
Okay,
discussed.
sir. Yes, sir. Sir, one doubt. See, if
Hmm.
we synthesize a compound,
Hmm.
doesn't take a XRD, but
Hmm.
just record the various NMR, like proton NMR, carbon 13 NMR, or
Hmm.
any other heteronuclei,
Hmm.
can we deduce the full structure of that molecule?
Why not? It is possible. See,
Hmm.
NMR can also give you the solution structure. X-ray and
Yeah.
others will give you solid state structure. Okay.
Okay.
You
Yes.
can get defined varieties of experiments are available
Okay.
in NMR, 1D, 2D, and in the 2D, homonuclear,
Yeah.
heteronuclear. Again, varieties of experiments are available.
Oh.
Appropriate choice of the experiment you have to make, and then you can get
Oh.
the structure. Okay, I just now in the
Hmm.
previously I told that to get the structure of any given
Hmm.
molecule,
Hmm.
I'll give you only molecular formula.
Okay.
No structure. I will not tell you what is its structure. Okay.
Okay.
I'll give you only simple one-dimensional NMR spectra.
Okay.
I expect you to give me the structure. Is it possible? Yes. Not big molecule, small
Uh,
molecules, reasonably using coupling constant and some chemistry, using
uh,
concept of chemistry, it is possible. You can get the
okay.
structure by 1D NMR also. For bigger
Hmm.
molecules, you need 2D. So what
Oh.
if you are you using 1D or 2D, madam?
I have not done any of this, sir, for a quite long time.
Okay, you do one thing.
Yeah.
You come to the workshop on March 7th and
Okay.
8th, which I am organizing on the NPTEL
Uh,
platform itself.
oh, okay, sir.
There, I will tell you by using 1D spectrum, how do you get structures, how to
Oh,
analyze
okay.
1D spectra, etc.
Yeah, I think her question
Okay.
is, can we get the structure from one
Yes, you will
NMR
get the
itself?
structure from 1D.
You can get the structure from NMR. You have to do 1D, 2D, sometimes
Everything.
3D. It does
Mm.
not matter how big the molecule is. And also you can get the
Oh,
3D structure from NMR itself.
Okay.
No need for
oh,
XRD. 3D structure you can get, where it is
You get
dihedral
cellulose
angle and where it's
structure, 3D
rotated.
conformation, and solid state, you will get solid, X-ray, you will get solid state structure.
okay.
Even we have NMR of solids also. To some extent, we also get the structure in solid state, not necessarily in
Oh,
solution.
mhm. Okay.
It is possible.
Sir,
Mm.
okay, sir. So most of this lecture, it is focused on the experimental data. Sir, theoretically, many people do theoretical calculations for a molecule, including they extract data of NMR also.
But
Now,
DFT,
how much? Yes, DFT have been shown. How much it matches?
it depends. Theory is theory, experiment is experiment. See, you
Okay.
can varieties of parameters are there. You can match it to some extent, but most of these DFT calculations can come close, but not give the accurate structure. At least when we
Okay.
did, we have not got that. But you get
Okay.
close to that structure.
Is there any interpretable program for interpreting the NMR spectra of huge molecules, sir?
Sandeep, you have an answer for it?
Yeah, there are many. Depends. For proteins, they have libraries. So if you
Oh,
put your chemical shift, it's set into that, and afterwards you see the chemical shift and match with that, you can get the
uh,
structures. There are many. Even for this, nowadays people do metabolomics. So
okay.
metabolomics, it's the taking the body tract like blood, urine, or anything, and then
Oh,
analyzing the components present into that. So no need to analyze one by
oh,
one molecule. Just you
mm,
upload your spectrum or chemical shift in a
mm,
software. Based on the
mm,
database, they tell you
mm.
what are the molecules are present into that.
Oh,
Okay, like that, there are many other tools like
oh,
softwares only. On your data, they will analyze near to
oh,
close your structure.
Yes, close to your structure.
oh,
Not exactly.
okay.
Maybe it is depends on many substituents or
Mhm.
something, but it will be very close to your structure.
Some are
After
even
that, you
public
have to
domain,
refine.
available in public domain also. Some of the
Yeah.
softwares are available
Oh,
in public domain also.
oh. Sir, can you give me some names of that?
I cannot give you offhand, but we can give you the
Ah,
next time when you come for interaction.
Next time we will tell
Otherwise,
you
you
some
do one thing,
softwares.
madam. Send an email to
ah,
me or Sandeep. We will send you.
okay.
You send
Okay,
an
sir.
email, we will tell you.
You have Sandeep's
Okay,
email or my
sir.
email, right?
Your email ID, it will come in the slide. Sandeep's, no, sir.
Sandeep, no. Sandeep,
Okay,
you
I will
can
write,
give.
sir. Huh?
He will write.
Ah,
You just write to
yeah,
us, and then we will
yeah.
give you names of the softwares. Often it is
Okay.
difficult to say, but what are available, whether the free, whether
Like
license is
one
available
Brookers,
free.
one Brookers is there, CMC.
Hmm. Correct.
That is Brooker
Okay.
CMC. So that is allowed. And also nowadays this allows people do analysis in Mestranova if you have
Spectrova.
Ah,
licensed version.
ah,
And for
okay.
depends on the your depend on your requirements, like it is protein, peptides, or simple molecules. It is different
Oh,
softwares. It's not like generalized one.
okay, sir.
You can send an email. Some of the
Yes,
available
sir.
softwares and their licenses, if it is free or not, will be given to you.
Yes, sir.
You can then
Okay,
go
sir.
ahead and get it.
Okay,
Okay, I
sir.
have sent my email
Yes,
ID to the chat box. Okay.
yes, sir. Yes, sir. I got it, Mishra.
Uh,
I see.
Oh, you have changed it, Sandeep.
No, this is
It should be
different one
sent to
because
EP or
no,
something.
that is different one, sir. That is almost filled. Actually, almost space is over.
Okay.
So I will manage that, but in this I can receive an email.
Yeah.
Uh,
Somebody has written,
This is an
whether chemical
alternative.
shift and coupling constant, how does it vary with the magnetic field? Who is that? Are you Nandini? Are you the one?
No, no, Del,
Who
somebody
is
Del.
who's
Del?
there.
Oh, is he listening?
Are you there, Del?
Del, are you listening?
No, he has posted a question. Okay. Sandeep, you want to answer? Shall I answer?
See, yeah, I can tell. See, chemical shifts, they are like it is normalized in the way it don't change for your understanding. Whatever the spectrometer frequency, it will appear as the same ppm. But if you are measuring in hertz, it definitely changes. Okay, because like if it is 400 megahertz, so 400 hertz is equal to 1 ppm. So ppm don't change, but if you're measuring in hertz, it will change. But coupling does not matter. It's which field you are acquiring, it will be the same.
You got it?
Understand, Del?
Is it clear for you?
Okay.
Yes, sir.
Okay.
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 Very
Okay.
good. If you
Sir,
remember,
I have.
chemical shift always changes with the magnetic field. Go to different magnetic field, you can see the spectrum will be appearing, it looks different because the
Valid
chemical
in
shift varies
hertz. In hertz.
in hertz.
But if you normalize
Okay.
into the ppm, it will
ppm,
be
it
same.
remains same.
Huh.
Whereas the coupling constant is invariant with respect to magnetic field. If the J coupling between two protons is 5 hertz, whether I do it in 400 megahertz, 1000 megahertz, whatever the frequency, it remains same.
Okay.
Are you
Sir,
okay?
Tell me.
Sir, there is one doubt. Now you told 400 megahertz is equal to 1 ppm. Now
No,
if you
not
take 8
megahertz, not megahertz.
Not megahertz.
400 hertz.
400 hertz is 1 ppm in NMR.
No,
Hmm.
it is at 400 megahertz spectrometer. 9.4
Okay.
Tesla. Huh.
Okay. In a 400 megahertz spectrometer, 400 hertz is 1 ppm.
Yes,
Yes.
If it is a 800 megahertz, then 800 hertz is 1 ppm.
1
Is
ppm.
it like that?
Exactly.
Yes.
Exactly.
Okay.
Exactly.
Okay, sir. This doubt was hitting like. Thank you,
Okay.
sir, for clarity.
I will explain to you whatever
Yes,
Sandeep
sir.
said. I will
Yeah.
explain to you in a
Yes,
this
sir.
thing. Huh?
Okay, sir.
In the chemical shift. Carefully watch it. Here I will
Yes,
show
sir.
you. See here, I made it for the benefit of you people. This one.
Okay, sir.
See, for example,
Hmm.
at 400 mega spectrometer,
Yeah.
we have used a reference, some different
Okay.
like TMS, etc.
Yeah, okay.
Then if
Okay.
sample peaks comes at 400 megahertz plus 400
Hertz.
hertz, the difference
Hertz.
in frequency is 400 hertz between these.
Hertz. Okay.
And that if
Okay.
you convert into chemical shift, this difference in the
Okay.
frequency should be divided by the
Yeah.
spectrometer frequency. This
Frequency.
thousand
Okay.
zeros you can cancel out. You get 4 over
Yes, sir.
4 million
Okay.
or 1 over 1 million. 1 over 1
Yes, sir.
million is called 1 ppm.
ppm. Yes, sir.
Parts per
Per million.
million.
Per
1 million.
million. Yes,
Same
1
sir.
thing if you do in 800 megahertz,
Yes.
sample peak, let us say, comes at 800
Yeah.
million plus 800 hertz. The
Certain
difference is
rats.
800. Okay.
Yes.
But if you do
Yes,
the
sir.
chemical shift, if you calculate like difference in the frequency by spectrometer frequency,
You
this
can
is
say.
1 ppm.
1 ppm.
You understood
Okay.
now? 1
Yes,
ppm
sir.
in 800 megahertz is 800 hertz. 1
Hertz
ppm in 400 megahertz is 400 hertz.
is one.
Now I will show you this one. For example, how I
Yeah.
do. Let us say I have two peaks, CA3 and CH2,
Okay.
coming at
Yes, sir.
450 megahertz and 900 megahertz. Hypothetically.
Hertz. Okay, sir.
Hypothetically. Now
Yes, sir.
spectrometer frequency is 300 megahertz.
Megahertz.
300 megahertz. So what is the
Hertz.
chemical shift of CA3 and what is the chemical shift of CH2? CA3 chemical shift is 450 divided by 300 megahertz.
300
Otherwise,
megahertz.
450 over 300 into
Comes
10 to the power of 6 is
with
1.5 ppm.
1.5 ppm. Yes, sir.
Whereas what is this one? CH2 chemical shift 900 divided by 300 megahertz, it is
Megahertz.
3 ppm.
3 ppm.
Okay. So now
Yes,
I
sir.
will give you here. Look at this one. For proton at 400
Yeah.
megahertz, 1 ppm is 400 hertz.
Hertz.
At 600 megahertz, 1 ppm is 600 hertz.
600 hertz.
At 800 megahertz is 800 hertz.
Hertz is
See,
800
what you have
hertz.
to do is, I'll show you here. Same thing for other nuclei, don't worry about it. Now you
Yes.
look at this thing here. I
Yeah.
look at carbon 13. At
Yes.
400, this is also too much. Then I have to explain gamma for you. Don't worry about that. Here, you remember this here, this one. If
Yes.
you have the chemical shift in ppm, if you want
Yeah.
to convert it into frequency, you have to multiply by the resonating frequency of the nucleus.
Yes.
If the value is in frequency, and if you want
Yes.
to convert it to ppm, you have to divide by the resonating frequency of the nucleus. Here, you have to
Yes.
multiply from ppm to
Apply.
frequency. From
Let's see.
frequency to ppm, you have to divide
You
by
have
the
to divide with
resonating frequency.
resonating frequency.
Okay, now I'll give you an example here.
Yes,
Maybe
sir.
wait, these are all like too many examples for you. Here, remember. No,
Okay.
this is also not there. Here, you remember what
Yes,
Sandeep
sir.
was explaining to you? If I
Yes,
explain
sir.
in ppm scale, 200 megahertz,
Yeah.
400 megahertz, 600 megahertz, 800 megahertz, whatever
Hertz.
the peak spectrum I take, same molecule, let's say,
Yeah.
the 1
Yes, sir.
ppm, 3 ppm, 6 ppm, 3 peaks. In
Mm.
200 megahertz, it is same, 400 is same,
Yes.
600 is same, 800 is same.
Same. Same.
Whereas if you come to frequency scale, this is 200, 600, 1200, 1, 3 and 6 ppm. At 400 megahertz,
Yes.
this is the value. At 800
Value.
megahertz, this is the value. See the
Value.
difference. As you go to higher
Yes.
frequency, spectrum becomes more and
Yes.
more resolved.
Alt.
Dispersion of the peaks become different. So now you look at this one. I have made this table. Consider a functional group X. Maybe X is
Yes.
something, I don't know. CH3, CH2, aromatic, whatever it is. If chemical
Yes.
shift at 400 megahertz is 2 pm, 2 ppm, 600 also 2 ppm, 800 also 2 ppm. Are you with me? Hello? Hello?
Yes, sir. I'm listening.
But you did not respond, so I thought you are not listening to me. Okay, okay.
No, no, I'm listening.
Okay. See, same thing. If another functional
Yes,
group,
sir.
if chemical shift is
Yes, sir.
4.5 ppm at 400,
Yes, sir.
same at 600, same at 800.
That's
Now coming to
800.
frequency, the same
Yes, sir.
functional group at 400 megahertz is 800 hertz, but 600
Hertz.
megahertz is 1200 hertz. 800
Okay.
megahertz, 1600 hertz.
This is
This is
sometimes.
where frequency to this thing matters. You will
Yes.
see this you have to follow my course where I have explained
Yes, sir.
everything in detail with number of
Yes, sir.
examples.
Okay, sir.
Are you okay?
Yes, sir.
Question? Any other question?
No.
You can ask question if you have anything. Still you have another 10 minutes time.
Dale, you have any question?
See, Sandeep is asking. He's keen to explain. You must ask questions and get your doubts clarified. No doubts? Nandini?
I have one basic doubt, sir.
Okay, ask.
Now, yeah, this nomenclature, Popal nomenclature of spins,
Hmm.
AB or AX. Sir,
Hmm.
can you little briefly explain how this coupling constant delta nu greater than J, that is greater than 10 hertz, it will be
No, not
AB
greater
or
than 10
AX?
hertz. That number is not right. There is a different
Okay, sir.
mechanism. Okay, there's the different way of
Okay.
explaining. Give
Yes, sir.
me 2 minutes. I'll explain to you.
Yes, sir. Yes,
I'll
sir.
open the slide.
Yes, sir.
Okay. I'll explain
Yes,
to you
sir.
what is Popal nomenclature
Lecture.
quickly. Because this one
Yes, sir.
we explain this, it takes at least 2 hours, but I cannot
Yes, sir.
give you that much time. In 5 minutes or 8 minutes, I'll explain.
Yes,
See,
sir.
you have to have a coupled spin system. What is a
Okay,
coupled
sir.
spin system? One proton may be coupled to many other protons with different
Mother
coupling states.
protons.
1, 2,
Yes,
1,
sir.
3, etc. Fine.
Etc.
Now, some coupling may be zero, doesn't matter. They are called coupled spin system.
Systems.
Okay, coupled spin system.
Yes, sir.
Coupled spin system, for example, in this case, this is coupled to
Yes.
this, this is coupled to this. Okay?
This.
But this is not coupled to this. So this is
This.
one spin system, this is another spin system.
System. System.
You are understanding me.
Yes, sir.
Now I will classify the coupled spin system into two, weakly coupled and
Yes.
strongly coupled.
Strongly
This
coupled.
is important to understand Popper nomenclature. But
Lecture.
which is weak, which is strongly coupled? Lot of
Yes.
explanation I have to give you.
Yes, sir.
That will take this itself to explain a lot of time. But simply remember this one. If the chemical
Yes, sir.
shift difference, that means there
Yes,
are
sir.
two protons are there, 1 and 2.
Yes, sir.
If 1 and 2 proton chemical shift is, let's say, very, very large
Yes, sir.
compared to J coupling. What do you mean by very large? Let us say chemical shift is 2000 hertz
Hertz.
and coupling is only 5 hertz.
Hertz.
What is that value? 5 over 2000 is how much? Very, very small, less
Very,
than
very
1.
small. One.
Then these two spins are weakly coupled.
Coupled.
If chemical shift is...
1 second, sir. 1 second, sir.
Hmm.
I will interrupt here. See, if you say weakly and strong, if after coupling signals are overlapped, means strongly coupled. If they don't overlap, means we can consider them as a weakly coupled. The simple. Is it right, sir?
No, I'll give a little
Okay.
bit explanation so that let her understand. See,
Hmm.
strongly coupled means couplings
Hmm.
and J coupling chemical shift difference are approximately equal to 1. I'll give you
One.
here example. This one, two protons are coupled.
Yes.
Here I
Yes.
can get the chemical shift. Here I can get the chemical shift of one proton, other proton, and this separation gives me J coupling. This is called a straightforward analysis. This is
Yes.
possible only when the
Yes.
chemical spins are weakly coupled. That means this
Right.
spin,
Okay.
this chemical shift, and this chemical
Yes.
shift should be very, very large compared to this one. They are very well
Okay, sir.
isolated, no overlap.
Yes.
As Sandeep said, there
Yes,
is
sir.
no overlap. They are weakly coupled.
Yes. Yes,
Now,
sir.
you consider these are all examples of weakly coupled. Consider a
Okay.
situation like this one. This is also weakly
Yes.
coupled. Strongly coupled.
Yes.
Strongly coupled,
Yes.
chemical shift difference is very much smaller than J coupling or equal to J
Coupling.
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 For example, like this. Here,
Yes.
compared to previous example, there were two doublets, one doublet here, one doublet here. It is
Yes.
easy to interpret,
Yes.
but here you do not
Okay.
know.
Yes.
And then as the coupling becomes stronger and stronger, chemical shift of
Stronger.
the couples will become much, much smaller among them.
One.
Then the spectrum becomes
Yes.
more complex, lot of
Yes.
overlapping would be there.
To there.
You
Yes, sir.
cannot analyze easily.
Silly.
Okay?
Okay, sir.
And all the peaks
Yes,
of
sir.
the strongly coupled are not of equal intensity.
Well, intensity.
Weakly
Yes, sir.
coupled, all peaks are of equal intensity.
Intensity.
Okay? These are all
Yes. Yes, sir.
non-uniform. They are non-uniform.
Yes, sir.
And
Intensity.
example for this, I don't want to tell you all. See, for example, this is a
Yes,
two
sir.
doublet. This is weakly
Yes, sir.
coupled. This is
Yes, sir.
again same two doublets appear like a
Yes.
quadrille. This is a strongly coupled
Yes.
systems.
Coupled. Okay, sir.
Now we'll come to your notation. That's what you asked me.
Yes, sir.
Each spin of nuclei we refer by alphabet, Roman alphabet.
Alphabet.
A, B, C, D, E, and up to Z.
Yes, sir.
Then when do you use this letter? Why? How do you use this letter? You have to understand it. The spins
Yes,
are
sir.
weakly coupled. The letters that are far away in the alphabet order is used.
Order. Okay, sir.
Okay.
Yes.
If the
Yes, sir.
spins are strongly coupled, letters that are close in the alphabet order are used.
Order is to be used. Okay, sir.
For example, weakly coupled means A and X spins. Strongly
Yes.
coupled means A and B spins.
And these spins.
Very, very strongly coupled means A and A prime. Chemical shifts are there, but
Yes, sir.
coupling is there. Even more strongly coupled is A2,
Yes, sir.
like that. So,
Right.
weakly coupled and strongly coupled, you have to explain like that. For example, I'll give you an example like AX, two spins are coupled. Three are coupled,
Right.
AMX. What does it
Yes, sir.
mean? AM chemical shift is larger, MX chemical
Yes,
shift
sir.
difference is larger, AM
Yes, sir.
chemical, AS chemical shift difference is larger. They're all
Jar.
far
Yes,
away
sir.
separated.
Right.
Coupling between A and M is smaller than chemical shift difference between these two.
True.
Coupling between M and X is smaller than the chemical shift difference between these two. Coupling between A and X is smaller than the chemical shift difference between A and X. They are
Index.
called weakly coupled three spin A, M and
Just
X.
a. Yes, sir.
Similarly, you can have four spin. Now, if I want to
Yes,
call
sir.
this strongly coupled, what change you will make for this letter?
It will be B.
Huh?
A, B, C.
Exactly. Fantastic. You understood. If it is
Yes,
AMX
sir.
weakly coupled, if it is ABC, it is
Yes.
strongly coupled. Even more
Right.
strongly coupled is AB to C or A to
C.
or A3, A prime, A double prime,
A,
like that. Varieties of nomenclatures you can start using. Okay.
yes, sir.
For
Yes, sir.
example, consider a molecule like this, three
Yes,
weakly
sir.
coupled. I have deliberately put different
Yes, sir.
halogens here, just to show that
Yes,
they
sir.
are far away. It need not be true practically. Hypothetically, I have written like
Yes.
this, so that this chemical shift, this and these are very well separated. These forms, what is called weakly coupled AMX system. In the Popen nomenclature, it is AMX,
AMX.
homonuclear. Same thing, you can also have heteronuclear with AMX.
Yes, sir.
So if you put AB, ABC, ABCD, they're strongly coupled.
Coupled.
Strongly
Yes,
coupled.
sir.
AB is strongly coupled,
Coupled.
ABC is strongly coupled,
Yeah.
ABCD is strongly coupled. Now,
Coupled.
let me not go into the more details of that. I'll
Good.
give you, oh, these are all too much for you to explain. Don't worry. If I start
Yes,
explaining,
sir.
you will take at
Yeah.
least 2 hours. See, I have
Okay, sir.
158 slides here to explain.
Okay, sir.
Each
Okay,
slide, if I
sir.
take 2 minutes to explain,
Okay.
it will be
Okay,
300
sir.
minutes. So it will take
Okay, sir.
4 hours at least. So I will not
Okay,
explain
sir.
to you. But remember, there is ways to understand how to interpret the spectrum using proper nomenclature.
Lecture.
I think this much is enough to understand.
This you understand. This is
Yes,
enough.
sir.
Or
If you
how
want
to
more, you
Yes,
can
sir.
call Sandeep or me. We will explain
Yeah.
over phone.
Okay, sir.
You call us over phone.
Yes,
This
sir.
cannot be written, explained by email. If you have doubts, you
Okay,
call
sir.
us over phone. We can
Yes,
explain.
sir. Okay, sir.
You have our number, right?
Yes, sir.
Okay, good. Very good. Anything else?
No, sir. This was the doubt.
Is it clear for you, madam? Everything?
Yes, sir. Yes, sir. Yes,
Good.
sir.
Now, in
okay,
this
then
concepts course, I have explained all these things. But of course, these are all detailed. I have not explained everything. What I showed in this
Okay, sir.
slide is I have kept on improving more and more with more examples.
Okay, sir.
But you will not find in the course. But at least the
Yes.
concept and idea is there. That you will follow.
Yes, sir. Okay, sir.
Okay, now the time is up. So
Okay, sir.
if you have no other questions from who is that Dell? Do you have any question? Dell. Dell doesn't want to ask any question, I think.
he just respond with no.
No?
No, he
No
wrote
more
no.
questions. Fantastic. So everything is clear for him. Okay, now if there are no other questions, Time is up. Shall we wind up?
Bharat?
Bharat,
Yes, sir, we can end this session.
we can end. Okay,
Yes, sir.
thank you very much. If you have any more questions,
Thank you, sir.
okay. If you have more
We'll,
questions in the
Okay,
next
okay.
session, after 1 month, we will be there. We will explain.
yes, sir. Thank you
Thank you.
very much, sir.
Thank you.
Okay, sir.
Take care.
See you.
Thank you. See you, Sandeep.
Okay.
Bye.